Hey team, Andre from High Performance Academy here. Welcome back to our first webinar of 2022. We're just getting back into the swing of things for this year, and we've got a lot of really cool content that we're looking forward to bringing out this year, along with a bunch of really exciting new courses that we're looking forward to putting out there. We know a lot of them people have been asking about for a while, and we're finally getting a chance to bring out some of the content that we've been looking forward to for a long time. Now, today we're going to be looking at a webinar on how to set up a flat patch, which is an interesting term. It really just means setting up a workspace that you can use to reliably and consistently do your alignment or corner weighting, or alignment and corner weighting on your race car. This is one of those aspects that on face value might not seem that important, and a lot of people simply skip this step, but particularly when you are doing your setups at a variety of different locations, different workshops, racetracks, etc. Covering off this one step is going to mean that you're going to get consistency in your results, and your car is going to handle more consistently and more repeatedly, regardless whereabouts you are racing. So it is something that taking the extra little amount of time that it does take to set up a flat patch really will pay dividends. Before we get into that, just a little bit on what's been going on over now what has probably been about 4 or 5 weeks since we broke up before the end of 2021, and I'm actually just fresh off a race weekend in our SR powered 86, which is pretty exciting. Hadn't got a chance to get that back out on the track since just before Christmas, where we did a little club sprint event at a local racetrack just down the road from us. That was pretty cool, but it was only a case of doing about 4 or 5 laps, and it was really time trial, so we weren't racing door to door with cars. We had an event here at our local racetrack, Highlands Motorsport Park, which was it ended up changing a little bit, was more endurance focused. Initially was going to be 1 hour long races. However, due to a lack of entrants, we ended up amalgamating with another field of muscle cars, and we ended up doing 4 half-hour races over the weekend. So not huge race distance, but what made it a little bit trickier was we were racing under some really hot conditions, the hottest the car has ever raced in, and that's one of the problems we did have initially with the SR turbo conversion, was keeping it cool. We've done a lot of work with the cooling system, and this is really around retaining the existing intercooler and radiator setup, and as well as the oil cooler as well, just as important for the overall cooling package. And we were working mainly there on proper ducting of the airflow in and out of the radiator, and that did seem to do the trick. And particularly with our endurance series racing, we did have no problems with cooling. The car was running comfortably in the mid to high 80s for a 1 hour event. However, that was coming off the end of winter, so we're sort of just coming into spring, so the conditions were obviously a little bit cooler. On the weekend, we were seeing temperatures as high as 37 degrees C, track temperature almost notching up to 60, and I can tell you from wearing a 3-layer race suit in a car with no interior fans and no cool suit, definitely wasn't that comfortable after a half hour of racing. So if we just jump across to my laptop screen, this is just a glimpse of what we had from a complete race session. So obviously a lot of laps all poured into one here, and really just what I wanted to focus on was the key ones that we're interested in here, which is our temperatures. And what I'll do, I'll just zoom out on a few of these probably less relevant groups of data here, just so we've got a little bit more sort of space for our temperatures. So what we've got here on the left hand side, we've got engine coolant temperature in blue, we've got our diff oil temperature in green, our engine oil temperature in orange, and our transmission or gearbox temperature in purple. So what we can see here is our peak values, which are really what we are most interested in. Engine coolant temperature 109. Not tragic, but definitely way hotter than I'd like to be running. Diff oil temperature, no problem there, 112 degrees. Our engine oil temperature, a little hotter than I'd like, but definitely in the ballpark. I try and run between about 110 and 120 degrees C, 121 peak there, but nothing too untoward, and it looks like it was holding quite nicely. And finally, our transmission temperature with the Hollinger, absolutely no problem there, 85 degrees C, and we can see it has pretty well plateaued. What you didn't see with this is obviously on the dash, I've got driver warnings coming up when our engine temperature goes above about 104 degrees C. And while I am the tuner and the driver, I can see the frustration that a lot of race drivers do face when they don't really care about the mechanical package and all they really want to do is race the car in front, because we did have that warning coming up pretty much consistently lap after lap over about 20 minutes of a 30-minute race. So you get pretty tired of hitting that reset button. Now, just a couple of little tricks here. You do need to be mindful of what you do with driver warnings, because obviously they are there for a reason. We, on one hand, want to bring the driver's attention to the fact that something isn't right, something that they need to be mindful of, and maybe this will allow them to take some preventative measures, which I'll talk about in a moment. So it is important. However, the driver is also concentrating on keeping the car on the track, optimizing their track position, hitting braking markers, apexes, and battling with other cars. You don't want unnecessary distraction on the dash coming up and taking the driver's attention away from what they should be doing. So there are a few tricks here. One of them comes down to you can program just about any aftermarket dash to step up the warning. So let's say, for example, what I mean by that is initially my engine coolant temperature warning comes on at 104 degrees C. If I then hit that reset button, it will bump the trigger point up by whatever I set, in this case 2 degrees. So it won't come back on until it hits 106. If I hit it again, it will bump it for a second time, but only a second time, up to 108. At that point, if we sit at 108 or above, it's constantly going to be coming back on. The other aspect that you can use with this is a reset time. So basically what that defines is when the driver presses the reset button, it will wait X amount of time before it will bring that warning up again. So you may want to warn the driver every couple of minutes or something of that nature. So that's just getting that balance. Every driver is a little bit different. Because I'm the tuner, the engine builder, and the driver, I do have a level of mechanical sympathy. So let's talk about those preventative measures. Because this was only a 30-minute race, I was prepared to run the car at a slightly higher power setting. We were running against some GT3 cars, some cars much faster than mine, particularly with a lot more power in a straight line. And that made getting a good run off the rolling start really, really critical. So what I was doing was using about 600 flywheel horsepower for the first half of the first lap before turning it down to around about 500 horsepower to circulate. And as that engine temperature warning started becoming more prevalent later in the race, I could then turn the boost back down further to reduce our power, as well as short shifting and all sorts of things like that you can do to help basically reduce the thermal load on the engine. So some considerations there around those warnings. But again, it does really come down to consulting your driver and having an understanding of what the driver wants to see, what the driver is expecting to see, while also safeguarding the mechanical package. As another element, I also always incorporate engine safety protocols in my tunes. So for example, there's a variety of ways that can work. A really simple one here is to start bringing down the engine rev limit as the engine coolant temperature exceeds, let's say 110 degrees C, which is what I've done in the case of the SR86. We can obviously also modify things like our fueling, maybe add a little bit more fuel, targeting a richer air-fuel ratio to help cool, reducing the boost pressure. So all things that happen in the background without the driver actually needing to be responsible. It's just that we do need to be a little bit mindful, because if you're overzealous with these driver protections, it can also make the car really hard to drive. And if you're in a train of traffic that's all going at about the same lap times as you, and all of a sudden you start getting an ignition card or your boost goes away completely, that can in and of itself be a little bit dangerous. Now I just want to quickly show a little clip from in-car. This is kind of what I was dealing with. So as I mentioned, the class was for basically GT3 or open GT cars, as they called it. So pretty much anything you want to come along and race, although we were aware that we were expected to be doing 1 hour long races with a compulsory pit stop. As I mentioned, we didn't have enough entrants, so they combined us with a production V8 and muscle class car. So the car up in front of me is an older Mustang. I am sorry, I am not a classic car fanatic, so I can't tell you exactly what year this Mustang was. What I can tell you is, after talking to the owner, it was powered by a 750 horsepower V8. It also weighed about 1600 kgs, and as you can see even from this shot here, doesn't have any aero, not a lot of rubber on it, and it goes pretty much as you'd expect. So at this point I'm running around about 500, maybe 550 horsepower, chasing this guy down during a practice session. Coming through the sweeper here onto the front straight, you can see I'm right back onto the back of him, go to the inside to actually try and go past him, and then power comes in and he just walks away from me. So we're coming up to a section here called the bus stop, which is a tight right left before we go into a very long sweeping right called the Southern Loop. Again, I'm just on a Sunday drive right now, sitting behind him, literally no stress on our car whatsoever. The point I actually almost hit the back of him because he had to get out of the throttle 3/4 of the way through the corner. Again, he just walks away from me down this straight. However, a little bit of pressure, that was about 2 laps of sitting right behind him, managed to pressure him into making a bit of a mistake. So there's always a way past, but certainly it can be a little bit frustrating when you've got a car that's really good under brakes, really good through the corners, but just lacks a little bit of straight line speed. I also managed to get past him in one of the races. I managed to just walk away because as soon as we hit a complex of corners, I managed to sort of put 50, 100 meters on him, and that just wasn't enough for him to make up during the race on the next straight. I think our lap times were around about 5 seconds different, so much faster in the 86, but it's also still a challenge just to get past. So a little clip of what was going on there. I will just head back over here to our photos and jump across to my laptop screen. This is a bit of a classic from Highlands Motorsport Park. We do have a bridge, so it's sort of got a crossover type circuit, and the bridge is sort of built to a point where if you've got a car that's fast enough, you will actually get airborne over the bridge, which always makes for some epic photos. I think unfortunately in this situation, this little left rear wheel was just maybe letting the whole team down a bit, but pretty cool when you're actually getting airborne, probably hitting that bridge at somewhere around about 180 to 190 kilometers an hour. Now, a little bit of Kiwi ingenuity that we did decide to have a crack at on the weekend with this overheating situation was a bit of a homemade water spray system for the radiator and intercooler. Obviously, we could only work with what we had available at the track, so a quick trip out to our local hardware store. We managed to find some garden irrigation components and also managed to steal a water spray pump off a local rally driver and basically put that into a 5-litre fuel container, jerry-rigged all of that and wired it up to the headlights, I think it was, or something of that nature, and managed to get that all working. So we ran that for the last race. It proved to be effective to a point, but because of the limited time we had, it wasn't run through a PDM, so it was manually activated. So it's a little bit challenging. I'm trying to activate that with my right hand while I'm going down the straights. And of course, I'm also trying to shift gears using the paddle on the same side of the steering wheel. So a little bit challenging, but probably managed to get us through the race with a slightly cooler temperature than we otherwise would have had. So there's always some options available to you. It just depends how ingenious and creative you want to be. Right, we'll just head back across to my notes for a second here. Now, one of the things that we came across while we were at the racetrack, the meeting was sponsored by a New Zealand supercar hypercar manufacturer, Rodin Cars, which is up in North Canterbury here, and they are building their own hypercar. I'm not quite sure when that's designed or intended to hit the ground. The intention, from what I understand, is to have a car that's as fast as a modern Formula One car. So there's certainly got an uphill battle ahead of them, but what they did do fairly early on was they bought the defunct Lotus T125 program, and they've got a couple of these cars that are up and running. I think one's in Europe, one is their current demonstrator, so we'll have a look over at my laptop screen. I don't really want to focus too much on the car, but there was a couple of interesting aspects that I did note. So this is powered by a Cosworth GP V8 engine. It was being driven on the weekend for demonstration laps by Liam Lawson, who's a New Zealand race driver who recently tested for AlphaTauri. So there's some chance that possibly Liam's going to end up in Formula One in the not too distant future if we're lucky. So really talented guy behind the wheel. He managed to reset the unofficial lap record at Highlands Motorsport Park. I think he lowered it by about 4 seconds, but probably no big surprise given the equipment he was racing. What I wanted to focus on here though was the use of infrared tyre temperature sensors. So we've got, I noticed this just sticking off the side skirt here. So it's on a nice little aerodynamic mount. So I'm not exactly sure of this particular unit. These can be analog voltage sensors, but more often we've at least been using CAN-based sensors, and they can have 8 or 16 channels that basically fires out a infrared pattern across the tread of the tyre and allows the tread temperature to be monitored. So I think I've got another photo, so you can sort of see how that sits in relation to, that's the left rear tyre. So we sort of end up with a pattern that comes out probably a heap straighter than what I've just drawn, but you get the idea. Now, why is that important? Well, what it does is it gives us information in real time about what is actually happening or how hard the tyre contact patch is working while the car is out on track. And that allows the data engineer to help optimize two aspects. The first of these is camber. So obviously we run some amount of negative camber when the car is stationary, and that takes into account the body roll, suspension compression and tyre deformation that we get when the car's heavily loaded in a corner. And what we're trying to do is essentially optimize that tyre contact patch while cornering. So if we've got that contact patch optimized, basically what that should mean is mid-corner, we're basically working the entire width of the tyre contact patch evenly. The amount we're working the tyre contact patch will be inferred by the temperature of it. The other aspect though that's also affected, will affect our tyre temperature is the inflation pressure. So if we've got the tyre overinflated, basically it blows up a bit like a balloon, and sort of something a bit like that, obviously exaggerated. So what we end up with is a hot patch in the center of the tyre, and the exterior, the interior and exterior edges run a little bit cooler. Conversely, if we've got it underinflated, we sort of get the opposite sort of situation, and it kind of ends up looking something like this. So we end up with a hot patch on the inside edge and a hot patch on the outside edge. So these tyre temperature sensors, they are reasonably expensive, although they have come down a huge amount in recent years, and they are a lot more accessible. They do require a little bit of effort in terms of mounting, but that effort can really reward you with the data that is delivered. Of course, when we're looking at the opposite end of the car, the front, this is the front tyre here, things do get a little bit trickier because understandably the front tyre does turn. What we can do there is take into account basically what we want to understand, which is the tyre contact temperature, patch temperature of the outside or loaded tyre in a corner. So if we're going around to the left, we want to be really focusing on the right hand front tyre, and we can look for some data for our steered angle and basically set the tyre temperature sensor up. So it's basically going to be getting a good shot at the tyre when we're under a moderate steering angle. So it's not perfect, but there are ways around that. All right, let me get back across to my notes for a second here. Now, I did want to mention, this may have slipped under the radar, we did release a brand new course just before the end of last year, which is our PDM installation and setup course. And we managed to coax Zac, who anyone who's taken our wiring courses will be well aware of. Zac's excellent in front of the camera, and he is absolutely perfect for a PDM installation and setup course. So if you've been hiding under a rock and you haven't heard the term PDM, power distribution module, I've got one here. This one is from Max ECU. You also may hear them called PMU, power management unit. Basically all the same thing. This is an electronic way of replacing your fuses and relays on the car, and it vastly simplifies your wiring harness design and installation. It also gives you a lot more control and flexibility in the setup. Now, what I'm talking about here is, let's say, for example, we've got a thermo fan that we want to switch on and off. Well, no big deal. Every car usually has that. Conventionally, we'd use an output from the ECU that would be hardwired from the ECU as an auxiliary output to a relay that would physically switch. There'd be a fuse for that particular circuit. It'd supply power to the fan. Nothing specifically wrong with that, but it is quite a convoluted path that we need to the power to go through, and there's a bit of work involved in wiring that up. With this, instead, what we end up doing is we use a single channel from the PDM, and that will go straight to our fan. Now we've got a variety of different ways we can control that output. We can still use an auxiliary output from our ECU, wire that to the PDM, and then trigger the fan in the same way. But where things get really smart now is that we can send CAN messages. So we can send a request from the ECU or the dash for that matter to the PDM asking for the fan to be switched on. It's not just that though. Where these PDMs get a lot smarter than our conventional fuses and relays is that if maybe something's just on the brink of failure, maybe our fan or a fuel pump is just on the brink of failure and the current draw is a little bit excessive. In a conventional system, if we exceed the fusing current for that particular circuit, it blows the fuse, job done. The only way of getting that car back up and running is to physically replace the fuse or maybe reset a circuit breaker and we can get back up and running. With a PDM, it's constantly monitoring our current draw. And if we exceed the current draw for a preset time, it'll break that circuit instantly. But then what we can do is also set it up so that it will wait a pre-configured amount of time and then it will retry that circuit a certain number of times. And that can be enough, that can be the difference just to let you limp back to the pits. So if we just jump across to my laptop screen here for a moment, I'll just quickly run you through the course PDM installation configuration. So you get a bit of technical background theory on what the PDM is, how it actually works. We'll learn about overcurrent and undercurrent protection, the logic functions, which is really critical because this is how we set up functions and how they all work. It's not difficult, but I know a lot of people new to PDMs tend to get a little bit confused by it. It's totally understandable. And what that confusion really spawns is a situation where I see so many PDM configurations that are simply only barely scratching the surface of what you actually can do. So understanding these logic functions is so critical. We'll talk about body control functions, we'll talk about the types of loads, half bridge and full bridges, outputs, PWM, pulse width modulated control, which some of these PDMs offer, soft start, etc. And determining the current draw, which is another obvious question we get asked. How do we know what the current draw in a circuit will be? It's not that difficult. We've got a practical discussion here covering some of the mounting considerations, working with large gauge cable, because we will be running a battery cable to it, batteries themselves and isolating the battery output, determining our channel current limits, paralleling outputs. What we'll find is depending on the particular connector, this is an AMP super seal connector. Each of those pins is usually only rated to about 8 amps thereabouts. So if you want to control something that is maybe 15 amps, well, how are we going to do that? Simple. What we can do is parallel two outputs and then wire them together to whatever we're trying to control. We talk about wiper motor control, starter and alternator control. Wiper motor control in particular, one of the most common questions that any ECU manufacturer gets asked about their power distribution modules. This is because wiper motors are a little unique and they also have a park switch. So if you want the wiper motor to work just like it does in your factory car, it actually has to be wired up and controlled correctly. We talk about CAN inputs and we also talk about PDM logging. I've also got some advanced case studies. So this is really showcasing some of the advanced functions that these power distribution modules are capable of, such as operating a backup fuel pump to automatically switch to a backup pump if the main pump is detected faulty, setting up a pit limiter with a rain light or a headlight flasher. You'll see this on a lot of race cars. Electric water pump control using pulse width modulation to control water pump speed versus engine coolant temperature. Also, alternator failure output prioritization. What I mean by this is if the alternator fails on track, what can we shut down? What is absolutely necessary to keep the engine running to get back to the pits versus other functions that are drawing power that we may be able to get away with just for half a lap or so to get the car back to the pits. Engine stall recovery, one of my favorites, and this is something we're using on the SR86. And this is a case of when the driver goes to leave the pits or goes to leave the start line on a standing start. If the engine stalls, the driver doesn't need to actually restart the engine. Simply depressing the clutch will automatically re-engage the starter motor. We've got a 6-step process for setting up our PDM and then a worked example library. So if you are interested in checking that course out, you can find that at hpaacademy.com/courses. As with all of our courses, it comes with a 60-day, no questions asked, money back guarantee. You also get 3 months of free access to our gold membership. It'll give you access to our webinars as well as our private members only forum. forum. Alrighty, last thing for today before we get started, I just want to remind you about the HPA Tuned In podcast. We're getting on with this thing now and I'm having a lot of fun doing it. We're up to episode number 22, which is interesting, labeled, Is There Such a Thing as Too Much Power? This was my chat with Oscar from Elmer Racing. Now, to give you a bit of insight into what Elmer Racing do, I just want to quickly switch over to a YouTube video. I'll just show a quick section of this. This is a tech talk that we did back at World Time Attack years ago. This is the RP968 Porsche, but it holds the outright tin top lap record at Sydney Motorsport Park and also the World Time Attack Challenge record. The interesting part from our perspective is that Elmer Racing are responsible for the complete Billet Thor 4-cylinder engine. This is rated for drag use at 3,000 horsepower and 10,500 RPM. Really interesting chat with Oscar about the design that goes into these Billet engines. He's currently working on a Nissan R35 GTR engine that will be capable of 4,000 horsepower. So if that goes ahead and it produces the power that Oscar's expecting, that might end up shaking up the R35 drag racing world just a little bit. So if you are interested, you can find HPA Tuned In anywhere you currently listen to podcasts, or check out hpa-tunedin.com. We'd love it if you could leave us a rating or a review. We're really interested to hear any feedback. We're trying to make this as good as we can and answer the questions that you as listeners want to hear. And we have some really great content coming up on that podcast over the coming few weeks. So check it out, please, wherever you currently listen to podcasts. All right. Thanks for your patience. Thanks for listening. Give me a few moments and we'll get stuck in today's webinar.
If you like that video, make sure you give it a thumbs up. And if you're not already a subscriber, make sure you're subscribed. We release a new video every week. And if you like free stuff, we've got a great deal for you. Click the link in the description to claim your free spot to our next live lesson.